During the previous lecture, we introduced a new type of spectroscopy that we called a two-dimensional spectroscopy, which used 3 pulses and a Fourier transform of the spectrum in order to get some sort of a two-dimensional plot, which we said was basically a absorption-emission correlation plot. Well, we will give this spectroscopy a well-defined name. We will call it two-dimensional coherent Fourier-transformed spectroscopy. This type of spectroscopy has its variants in, let's say, visible, where it addresses electronic degrees of freedom of molecules and atoms, and it has its variants in, for instance, infrared wavelength, which addresses the motions of nuclei, for instance, molecular vibrations. So we will now make a little summary of the method, and then we'll go and have a detailed look at how it is measured. We also have 2 problems that we have to solve. The fact that in order to really realize this experiment, we have to be able to detect complex signal, and we have to be able to fix its phase. So let's start with a summary of the method. So the method is based on the third order response. So it's an analysis of a third order response. This often would be a problem because if the signal comes bundled with all other orders, we would have a problem. But we know that we can, by devising specific directions of the 3 pulses, we can get a background free response, so we can really isolate the third order response from everything else. Its interpretation is that it correlates absorption and emission. So we absorb on certain wavelength and we emit on certain wavelength. These 2 events, absorption and emission, are interlinked by the evolution in the molecule. So if you excite the molecule at one state and the population, the probability that the state is excited travels to another place, to another state, then the next event happens from that state. The emission event happens from that state, and this is how we can observe the correlation between the 2. We correlate the wavelength at which we excite with the wavelength at which we emit. And of course, this what I just described is that the correlation is mediated by excited state dynamics. So by this method, in principle, we can observe excited state dynamics. That's the purpose of this method. That's not something completely new because, for instance, the pump probe method has also been able to give us information about the excited state evolution, for instance, transfer of the population from one state to another. Now, it's very important that we realize that there are, of course, some sort of limits to this information or to this basic information about the pump probe spectroscopy. So we'll make some notes. For instance, we know that we have so-called Liouville pathways, and some of them go through the excited state. So there is really a contribution which follows the excited state dynamics, and there is also a ground state evolution. There are pathways in which during this middle interval, the interval between the second and third pulse of the method, the system is in the ground state, and there it does not evolve. And this type of response, which is static in that it does not evolve in this time, in the length of the interval between the second and third pulse, this has to be also taken into account. So there is a static ground state signal, And we have to know that it is there, and we have to see how it combines with the rest. And of course, the emission that we see, the emission of the signal, has the phase, or it has an arbitrary phase in our measurement, but it has both components. It has the phase that corresponds to absorption of some signal, and also to an emission of signal. In case of stimulated emission, for instance, we really emit a signal, but we have also ground state bleach, where in fact the signal that we see corresponds to a lack of absorption, for instance. And we have excited state absorption, which is some additional absorption of the system, and we recognize the type of the emitted signal, whether it corresponds to emission, absorption, excited state absorption, etc. We recognize this only by phase. So emission has some sort of a generalized meaning here, because we always emit, but we have different components. We have different components of this emitted signal, and they correspond to stimulated emission, excited state absorption, and ground state bleach, and they differ by phase. So it is very important that we are able to actually determine the correct phase of our signal. So we have to take these things into account when we try to understand what type of spectroscopy we have actually constructed. Its interpretation is not completely straightforward when it is measured without the background. It doesn't give us almost anything automatically. We have to process the signal in a very specific way, and we have to understand how the signal is built. So let's see first, how is this 2D spectrum measured in details. So of course, as always, we have a sample. So this is a sample in which we have the molecules. This sample has a specific width and so on. And now we want to send 3 pulses from 3 different directions, and we want to get, and we know that we will get a signal out. Actually, we also know that we will get the signal in all possible combinations of the directions of the k vectors of the pulses. So we need to know like where to look for our specific signal. So one way to arrange this is, for instance, the following. So we set a square here, and we send the pulses to our, let's say, the center of our sample through the edges of this square. So we will have, for instance, a pulse coming like this. We will have a pulse, well, this unfortunately does not really distinguish well between the directions, at least these 2 here. So we could in principle send signals through all these edges, and we get the signals coming out on the other side, where they obviously also create a square. So now we have to realize how it comes out. So for instance, this is from the bottom, so it will be up. Here this one is also from the bottom, so it will be in the upper part. Then this, let's say, can be from the upper left, so it will be bottom right, and we have to have one more signal coming to this direction. Okay, so there has to be one of them going here. Okay, so with this imprecise picture, you probably now understand what's going on. So now let's have a look at our expected signal. So we want to see where is the Ks. That's the direction of the signal, which goes into minus K1 plus K2 plus K3. The best way to understand that is to draw this. So let's use the same color, the same square, but directly face it. And here we can draw the directions easily. So we send in 1 pulse, 2nd pulse, 3rd pulse, and there is a fourth direction. So these are the 4 directions we send things in. And now we ask ourselves, where is this pulse that is sent from this edge, where it is appearing in the second square behind the sample? And that is best understood when we start drawing these k vectors from the center. I mean, we are looking when we face the square from this side and look through the sample to see the other square. They are actually they cover each other. We forget all the perspective and all these things here. When we look at it, we can safely and perfectly ignore the main direction of the pulses, which is from right to the left, and we are looking only at the component projection of the direction in the plane that goes through the sample, perpendicular or almost perpendicular to the pulses. So we can start drawing the k vectors from the middle out to the edges. So for instance, let's say that this pulse here will be the pulse 1. So now I'm supposed to draw it from the center, and if we were drawing K1, then it would go all the way to this place here. But we don't want that. Actually, we are not actually looking at K1, we are looking at minus K1. So we start from here, and minus K1 ends up here. Now, K2, let's say that the second pulse will be this one, then K2 goes from here to here, and K3 goes from here to here, and they exactly cancel each other because they go different directions. So altogether we can see that the signal appears at this place. So this is the direction of the outcoming signal, Ks, and with this we also have to write the 3 here, and we want to send in the same direction the local oscillator. So this is the local oscillator then. This is the local oscillator. So this is how we do it geometrically. If we go back, we can start writing which pulse is which. So according to our picture here, this is the K1, this is the K2, here we have K3, and from this direction we send the so-called local oscillator, which is another pulse with which we will mix the signal with. So just also to be sure where the signal goes. The signal goes from here to here in this picture. Okay, that's it. That's how we can organize the pulses in space. So this is the geometry of the experiment. This is how we measure it. We send in pulses from the direction K1, K2, K3, and the so-called local oscillator. Interestingly, we sense the local oscillator usually way earlier than all the other signals. We'll try to see why that is, or let's say we can ignore this question because it's a completely experimental question. It's true that it is usually sent as the first pulse, and if you ask why it actually does not interfere, or why we do not, for instance, have a fear that this works as another pump, well, that's because we are measuring third order signal, and if you look at the direction at which this third order signal would have to go, or what kind of frequency it would have to have, well, the direction of the signal might be Ks, because local oscillator goes in the direction of Ks, but let's say combining these two pulses together in that direction would, for instance, lead to signal with 2 omega, etc. So thanks to the nice concept of perturbation spectroscopy, by the fact that all the nonlinear signals correspond to some specific perturbation series or specific perturbation order, we don't have to worry about an additional pulse in our experiment. Okay, so that is the spatial organization of the pulses, and now we may ask about the pulse order. So order of the pulses, I mean order in time, and there we have two options. I mean, we always want to measure in the direction minus K1 plus K2 plus K3, but we know that if we send the K1 pulse as first in this direction, we are going to get the so-called rephasing signal. So let's take first time axis, then let's set pulses on it. So we will have time 0 here with the pulse K3 coming, and before it we have two other pulses. They come with the order K1, K2, and here we have the delay tau, and this is the delay t. Okay, so that's an order which gives us the signal that is the so-called rephasing signal. These are all pieces of information that we have already discussed in earlier videos. So sigma r, that's the signal, and the way it is detected, we measure it, or we have postulated this signal as frequency dependent. So we will measure it frequency resolved, and it depends on capital T and tau, the delays between the pulses. Then the second thing that we can measure, if we stick to the same direction but just switch the order of pulses, namely the first and second pulse, those that have different signs, so to say, in the way that they combine in our experiment. That's how we can actually distinguish them in the experiment. So the K3 is the same, but we can measure the situation with K1 pulse coming after the K2 pulse. So we now define tau as a difference or delay between these two pulses, but reversed, and capital T is still the difference between the second pulse that comes and the last pulse. And in this situation, in the direction minus K1 plus K2 plus K3, which is the one that we have marked with blue here, in that direction we get the so-called non-rephasing signal, which is measured basically exactly the same, just the order of the first two pulses is different. So this is non-rephasing signal, or non-rephasing two-dimensional spectrum. So these are also spectra. Okay, how is this detected actually, and what is detected? This is how, if we remind ourselves the previous lecture, this is how we define the spectra, but how do we measure them? I mean, I've been describing how we generate the signal that we want to measure and what it should correspond to, but we haven't yet discussed how we measure it. Well, we measure it in such a way that we take the signal, so this is the detection of the signal. So we send the signal in, then we need to frequency disperse it, so we use some grid or something like that, and the signal goes spread in frequency to some sort of a CCD detector or something like that. Again, we do not really want to be completely exact, so there's gonna be frequency resolved detection with some CCD device, for instance. So what we get from that is a simple picture where we have omega, and well, we see how much we of course absorbed in the CCD in different frequencies, so we get a picture like this, for instance. But what is it? Well, that is, again, if we remind ourselves the results from the previous lectures, this is a real part of, for instance, if we measure with the pulses so that the signal is rephasing, of the sigma r omega t tau, but also with this unknown phase. So this is actually what we measure. This is what we measure, and the question is, can we actually really fix the phase correctly, and can we measure it so that we can fix the phase under the real part? That is, we would actually have to have a full information on the complex signal, or can we somehow restore that information from what we have. So we measure this, the rephasing or non-rephasing signal. Both can be, of course, measured because it depends only on the order of the pulses. But this is how we actually really physically can get the curve corresponding to this particular setting of capital T and tau. Then we get one frequency resolved curve. And in fact, we can collect many such spectra. So let's say if we have omega here, this is the so-called omega T, because it's the frequency that corresponds to the real time. And here we have, for instance, here we have tau, and we measure many curves like this for different values of tau. I mean, this is not a nice plot, sorry, but we measure all these things so that we get some sort of a two-dimensional spectrum already. But in order to get the signal, we also need to perform a Fourier transform on this tau t. And all that we would ideally do with the complex signal, because the real part would almost definitely not give us a chance to get rid of a complex factor like this. All right. So now we know what the experimentalists have to do in order to collect the sort of initial data for processing to get the complex signal. And now we want to show how they actually solve the two big problems that we have identified so far, namely, and both actually related to the complexness of the signal, namely how to get the complex signal out of this real part and how to repair the phased problem. So two problems to solve are: one, how to measure complex signal, and two, how to fix the phase. Both are questions. All right, so let's go to detect the complex signal. Detection of the complex signal. All right, so let's ask first why we even want the complex signal. So why complex? Well, the answer is because we want to add sigma r and sigma nr. We want to add sigma r and sigma nr. That's because when we add them, we get a real function of tau. And when we add the rephasing and non-rephasing signals, we get a real function of tau, which corresponds to, as a function of tau, it corresponds to the absorption line shape. It would be as if we measured absorption. This is all related to what we have done in earlier lectures. So if you don't understand what I have just said, you have to go back and try to understand how the signal is composed of different contributions. So this is why we want to do it, and it's extremely important then. Well, if we don't have a correctly built complex signal, we cannot add these, so the real and imaginary part of it, to give us another sort of correct real signal. All right, so if we know how to do that, how can we actually proceed? So we proceed by realizing that these sigma r's and sigma nr as a function of tau, that they look like absorption response. Actually, we will get the line shape if we combine together the sigma r and sigma nr and then Fourier transform them. So as a function of tau, they have a form of absorption response, so the response function that corresponds to absorption. So sigma r omega t tau would look something like this: e to the power of I omega Eg tau, where this is the optical field with the frequency omega Eg. And in order to actually calculate Fourier transform, we would need a function that looks like this. And in fact, we measure a real part of it. Yeah, because we measure a real part of sigma r, again, with some phase, etc. We measure it as a function of tau, and we measure the real part. So what is that real part? That real part is roughly, not roughly, real part is a cosine of omega Eg tau. Okay, how can we get back, that's basically our issue, how can we get back the e to the power of I omega Eg tau from cosine? So how can we get e to the power of Eg tau from cosine, like this? So this is nothing impossible. So this is actually perfectly possible. If we had cosine, we could get e to the power of omega Eg by realizing that cosine is just a sum of two exponentials. This is 1/2 e to the power of I omega Eg tau plus I minus omega Eg tau. And what we want to do, we want to do this reconstruction of the e to the power of I omega Eg tau on the signal. We don't have the idealized situation here that we have a cosine. We want to get that with the real signal. But how can I get a decomposition of my signal into these cosines? Well, that's Fourier transform, nothing else. So I have a signal, even if it's a real signal, and actually especially when it's a real signal, when I put a Fourier transform on it, I get a decomposition into, well, either cosines or actually even already into the complex exponentials. So the procedure would be the following. I take a real signal, and I make a Fourier transform on it. I perform Fourier transform, and I'm getting a spectrum, and I'm getting this spectrum because the signal is real. I'm getting it for positive and negative omegas. So I am getting a signal at omega Eg and at minus omega Eg. So this is a real signal, and of course it has the omega Eg frequency, fine. And I'm getting two delta functions in this situation at the frequencies omega Eg and minus omega Eg. And because the signal is real, I'm actually getting them exactly the same. It has to be, it's like this here. I have to have the same amount of e to the power of I omega Eg tau as e to the power of minus I omega Eg tau in order for my signal to be real. So this is the situation of the cosine. Real signal would have it slightly more complicated. Real signal, in real signal it will look so that I will have some sort of a decaying exponential. I have some sort of a decay. Fourier transform will give me a contribution centered around omega Eg and centered around minus omega Eg. And if we are at optical frequencies and decays are sort of normal as they should be, we will get two separate distributions of frequencies, one around omega Eg and one around minus omega Eg. And these two together, they actually make this real signal. But if you cancel one of them, interestingly, if you cancel one of them, you can easily get a complex signal because you are canceling one. Let's imagine that we cancel this part of the cosine, so that would mean we cancel the negative frequencies and have only the positive ones. The notation is such that if we go to minus, that's the positive frequency. E to the power of minus I omega Eg is the positive frequency exponential, complex exponential. So if we delete one branch, one symmetric branch of the real signal, Fourier transform real signal, and Fourier transform it back, we are actually getting a complex signal. This looks completely artificial. In fact, it is completely artificial. But again, we know that the signal is real, so it has to have these two complex wings and nothing else. They cannot be different. So it's no problem if I identify it by Fourier transform, as long as this is a correct Fourier transform of that real signal. Okay, so the procedure for processing the data from our spectroscopic method, so that's almost an experimental data processing procedure, is taking what I know in theory is a real part of sigma r omega t tau e to the power of I phi, Fourier transform it into a function that, well, let's call it Fourier transform of the real part sigma r omega t e to the power of phi, like this. This is a function of omega tau, and it has two peaks around omega eg and minus omega eg. So the next step we'll do is remove e to the power of minus I omega eg tau. So after that we get basically, well, let's do it like this. What we get is we kill this part, and the next step, the last step of this procedure, is that we Fourier transform the signal back. So we make an inverse Fourier transform, and the result of this Fourier transform is sigma r omega t. This is a Fourier transform of this function of tau, and we get omega tau. So here's sigma r omega t tau e to the power of I phi. So we have reconstructed the complex rephasing signal. Now we have to do exactly the same procedure with the non-rephasing signal. The same procedure has to be done with non-rephasing signal, and then using that we combine finally everything into the two-dimensional spectrum. So this is two-dimensional Fourier transformed spectrum, and that is, as we already said, that's sigma omega t omega tau. That is integral. So here we make a Fourier transform with in tau of the real part. We still have the phase here, and we Fourier transform like this with minus. Okay, so we are removing the minus part, leaving just the plus part, and therefore the Fourier transform can look like this. Okay, the non-rephasing part contributes in the following way, and r omega t tau. We have the same problem with the phase, and this time we Fourier transform with e to the power of I omega tau tau. That means that we actually preserve the minus part of the two wings of the signal that we obtain by Fourier transforming the real signal. So here in the non-rephasing part we are removing e to the power of I omega eg tau part. All right, these two contributions here we can collect into one. There will be a prefactor e to the power of I phi, and then integral from minus infinity to infinity, and we put here the Heaviside step function so that we can write the rephasing part, which originally had the integration only from 0, and we add to it with the minus theta function the non-rephasing part, but because we still want to have positive taus, we can place them here like this, and we keep e to the power of minus I omega tau tau. So when tau is negative, we are getting, in this case, the second integral. We can easily see that this altogether gives the same result. We have to handle also the situation in the middle. We can, for instance, set that the Heaviside function at tau equals 0 is equal 1/2. Okay, so now we have a procedure how we get from what we measure some sort of complex signal. We give it a subindex m because this is the measured one, which is wrong by the unknown phase factor e to the power of I phi. And now the big question that we have to answer is how to fix that phase factor. So let's do this, fixing the phase phi. And for this task, we start with trying to get an information or trying to compare this measured signal with pump probe, because we know that in pump probe we do not have the phase problem. It is handled automatically because the generating or the inducing pulse, that is the pulse which induces the signal in the sample, well, it has an arbitrary phase, but its generated signal has a correct or automatically correct phase relationship to its generating pulse. So we compare what we can see in pump probe and what we can see in 2D spectroscopy. So how does sigma omega t omega tau, that's what we have now constructed, and pump probe signals compare? We are looking for how to put these things next to each other, trying to find out basically if there is a way how we fix this unknown phase by looking at pump probe. So usually there is a different sign convention between the two. So there is a different sign convention. If we take the real part of sigma omega t and omega tau, this is roughly minus pump probe spectrum, roughly. The conventions are such that here in pump probe, stimulated emission, that is stimulated emission, is negative, and here we have stimulated emission positive. That's a difference which we have to make sure that we take into account when we compare the two spectra. The second thing is that there might be various prefactors that originate from, for instance, the Maxwell equations. So some prefactors such as omega divided by an omega, the refractive index, but these things can be removed. That should be fine. Can be removed. We have so far defined the sigma, the spectrum, basically as a sum of the Liouville pathways, the contributions of the Liouville pathways, in which case we would have a prefactor that has to be handled. All right. But the third, the most important relation, which is related to the other two or uses the two but is more specifying, is that in fact the real part of sigma omega t and at tau equal 0, that is the signal which we have now Fourier transformed, but if we Fourier transform it back, so that's Fourier transformed of omega tau, if we Fourier transform it back to tau and set tau equal to 0, we will actually get almost precisely, again it's up to the prefactors from the point 2, the minus pump probe. At least in our theory it was so that we calculated the pump probe basically as a sum of rephasing and non-rephasing pathways at tau equal 0. So it is a sum of rephasing and non-rephasing pathways at tau equal 0. Unless it's all Fourier transformed, let's say detected in by Fourier transform, so that's why omega and capital T is a delay between the second and third pulses of this 3-pulse scheme, or in pump probe it's a delay between the pump and probe. Okay, so this last thing is the most important, because now we can actually write out how this real part of the sigma at tau equals 0 looks like. So this is minus pump probe. Now let's say we have already stripped it of all the prefactors, so we can say this is the real part of sigma omega t tau equals 0, and that is the real part of, let's perform the Fourier transform back. Omega tau, and here e to the power of I omega tau, and we should have tau here, but tau is supposed to be set to 0. So altogether this is real part of the integral over all frequencies sigma omega t omega tau and nothing else. So minus pump is equal to this. So that means the measurement of the sigma could be done the following way. So we measure sigma m, which is basically e to the power of some unknown phi sigma. That's the first step. Second step, we measure pump probe. Let's that be, for instance, S of omega. This is also of omega. Let's assume we are at certain value of capital T. So we measure these two signals, and we should also add that we integrate sigma m over all omega tau. So we get one line, one function, which will be some sigma tilde of omega. And now we compare this, let this be some sort of a function which describes the minus s omega. This would be obtained from pump probe, and next to that we can get, I don't know, it might look for instance like this, some other function which will be this sigma tilde omega, and this has to be the real part of it, real part of the sigma tilde. And in sigma tilde we have, inside it we have the e to the power of I phi factor. So that includes this factor. And we can vary, we can fit the two spectra on each other, so that for certain value of phi we get an agreement. That is basically how we fit the spectrum. So once we know the phi, we can say that the spectrum, the correct spectrum is I to the minus I phi that we obtained, sigma measured tau. So this is it. So we get a certain value of phi, which basically allows us to fit this real part of sigma tilde onto minus S omega, which is the pump probe measured signal. So experimentally, we would perform all this complex evaluation of the data from the 2D spectra. Then on the same setup, we would measure pump probe spectra, which basically amounts to measuring with one pulse, not with two pulses, and measuring differential absorption in the direction of the probe. And these two spectra have to be compared so that the complex spectrum is integrated along its omega tau axis and then compared to the pump probe. All right, so this would be the procedure, how we basically not only determine the complex signal that is done by a trick, assuming that the real signal has two wings that are equal and basically forgetting one. And the second task that we had is fulfilled by comparing the integrated complex spectrum against the pump probe and varying this free phase that we have there until we reach an agreement between the two. So once we have that, we have a true 2D spectrum, which has a good interpretation. So after the phasing procedure, that's basically what I have just described. After this phasing procedure, we have a spectrum that has the following interpretation, that it's a real part. Sometimes we use omega t for this real part, has a good interpretation as an absorption emission plot. And we can of course also have the imaginary part. This spectrum has an imaginary part, and that imaginary part is not completely useless. We don't have such a good interpretation for it, so no good interpretation. It cannot be compared to any other standard experiment in the way that the real part can be, but you can fit it as well. It's an additional information. You measure it and you model it. You can calculate imaginary part and be more sure that the calculated signal is correct. Moreover, sometimes the imaginary part shows some interesting features that can be localized or fitted better than the features in the real part. In the real part, we have peaks, which look like absorption peaks and so on. In the imaginary part, we would have nodal lines, for instance, and nodal line can be very well localized because you can easily find a place where there is a zero in your spectrum. So in a particular case, it might have quite some sense to also look not just to the real but also to the imaginary part of this 2D spectrum. Nevertheless, the procedure always has to contain some sort of phasing. So when you measure 2D spectroscopy in this particular setting, you also have to measure pump probe, if not for nothing else then just at least for setting the correct phase of your signal. Okay, so with that we have completed a discussion of the method without actually so far calculating or showing any example of it. So that has to be repaired now, and in the continuation of this video we will have a look at the simplest situation, and we will be trying to figure out how a 2D spectrum is actually monitoring energy transfer in a simple system of two molecules. One of them would be a donor of energy, would be excited, and then it would donate the energy to the other, which will be called an acceptor. Okay, so let's be practical now and try to turn everything into some calculations. So we'll be looking at a dimer, two molecules, as was already said, donor and acceptor molecules. They will have the following states. This is, let's say, the donor having its ground state and excited state, and there will be an acceptor, and it will have a smaller energy gap so that it can thermodynamically be expected to be populated preferentially. So it also has a ground and excited state. So this is the picture of the system. There's something missing. We will assume one directional energy transfer. So once the excited state of the D molecule is populated, it will transfer the energy to the excited state of the acceptor molecule. And we will assume that the coupling which couples the two molecules is relatively weak. So there will be dephasing of optical coherences on the two molecules, and there will be energy transfer. But we will not see other effects that one could expect in such a donor-acceptor system, for instance, level repulsion and some sort of emergence of delocalized states. That is not going to happen here, although as always, we can assume this donor-acceptor system as one system and look at its collective states. So collective states of this system will be a collective ground state. Collective ground state means that both molecules are in the ground state. We also assume that there is a state A, which is the situation in which the molecule D, the donor, is in the ground state and the acceptor is in the excited state. State D will assume that the donor is excited and acceptor is in the ground state. And we will also assume, although this state will not be reached in the third order spectroscopy, I mean reached in a meaning that we will not have to look at the time evolution of this state. We still have to add the state F, which will have both the donor and acceptor excited. Why I was a little bit hesitant to add this state, the thing is, if we populate, for instance, the excited state of the donor, we cannot expect that somehow that energy, well, there will be basically no way how we could populate the two states ED and EG at the same time in that form, because such a state would have an energy that is a sum of the two energies. And we have a conservation of energy in this system. Why we can cross a small energy gap like this one? That's because we have environment surrounding all this which can accept some of the energy and basically dissipate it. Okay, nevertheless, we will see that in the spectroscopic response, we will also need to consider the state F, which will be populated eventually by, or could be populated by, the sequence of pulses in the experiment. All right, so what we will need these states. We will also need a description of the excited state evolution. So description of excited state evolution. We will need it because we know that in some of the Liouville pathways that can potentially open in this system, we will have to propagate the system in the excited state. So we have the following elements of the evolution superoperator. There will be an evolution which will bring the population of the state A, that is density matrix with these two indices, back to the same state. So the following element of the evolution superoperator will be present. So this is an element of the evolution superoperator. And this particular one governs the population of the excited state A. There is, of course, a similar term which would have 4 indices. D, which brings the population of the state D to the population state D, and then we have evolution, which governs the energy transfer. We have energy transfer from donor to the acceptor, so we will have to have a non-zero element AADD. These states count from right to the left, so this is a non-zero element, and there is also, so this will be the energy transfer from the state D to state A, and we also have some possible evolution of a coherence between the states A and D. So this is the evolution of coherence, meaning coherence elements, that is off-diagonal elements of the density matrix, reduced density matrix to be more precise. Well, now with all these states present, we, as every time when we want to calculate a nonlinear spectrum of any type, we want to list and describe and evaluate Liouville pathways through this system. So let's have a look what all Liouville pathways we can identify in this problem. So we are looking at this dimer with energy transfer, and we are looking at its Liouville pathways. They will always come in pairs. We know already that there will always be a rephasing and non-rephasing pathways coming in pairs, and there are processes that we observe like stimulated emission, ground state bleach, excited state absorption. And another important observation is that except for the energy transfer governed by some rate KAD, that is the energy transfer from donor to acceptor, if we would ignore that, we would get a response of 2 independent molecules. So we can, for instance, have a look at the stimulated emission of the molecule A. That will give us rephasing and non-rephasing Liouville pathway, this type of process. All right, so the Feynman diagrams of the rephasing part, they always start with an excitation from the left, and because this is on a molecule A, we will start with this optical coherence. Second pulse will have to, because this is a stimulated emission, it will have to bring us to the excited state, and because we are on the molecule A, it cannot be anything else than the A. And well, the diagram has to end with this wavy line on the left hand side, where it converts the A to ground state. So the only change that we can do here with the third pulse is basically that we de-excite this thing and we get another optical coherence and we end up in the ground state. So this is certainly a good Liouville pathway for the stimulated emission signal, because we went through the excited state of the rephasing type, and we have to complement this by the non-rephasing pathway, which looks basically the same, except that it starts from the left. Okay, so when it starts from the left, it has to complete population by interaction from the right hand side, and then everything has to proceed like in the non-rephasing part. So there will be A here and a wavy line. Okay, so this is how it proceeds, and we can actually start looking at the Liouville pathways that we get here. So we will have a prefactor of dA, transition dipole moment, from the ground state to the excited state on the acceptor molecule to the fourth power averaged over all directions. And now we should have those two coherence intervals represented by, we can actually already represent it by this complex line shape. For instance, the third interval, which will then be Fourier transformed into omega tau, we will represent by the complex line shape AG, omega t. In the middle interval, there will be an evolution from A to A. So here we have, let's say, tau, t, and lowercase t. And here we would have at the end, like basically the first interval that we should have written, there are two complex conjugated contributions. So if we sum them together, we get a real part of g a g omega tau. So this is how the contribution of tau of the first interval can be turned into the absorption on the state A or to the state A. There is a time evolution in the middle because we assume that during the time t nothing else happens. Then let's say the population or some coherences not optical type, they proceed in time t. So basically there is only this simple element here, and that connects us then with the emission process that happens in this third interval, and we detect this in a complex manner. So here is a dot, there is a multiplicative factor. So this is how the stimulated emission on the acceptor contributes. We can also say that because the acceptor is not going to de-excite in any way, that the UAA is equal 1. Then we have ground state bleach on the acceptor. Ground state bleach, that's a signal which originates from the ground state. So we also have a rephasing and non-rephasing contribution. So the beginning of the rephasing contribution has to be exactly the same as above. So it's going to be this, but the second pulse will not bring me to the population of state A, but will bring me to the ground state. So it has to look like this. Now it's obvious that UGG is 1. There's no evolution on the ground state. It is not the evolution of the population. And because this is a rephasing pathway, it has to sort of end up exactly the same way as the rephasing pathway of the stimulated emission. So we have to first excite A here and then send it out by the wavy line. All right, and this is plus the non-rephasing contribution, which corresponds to this rephasing one, and they should differ only by starting from the left. So it has to be like this. Here we are back to the ground state, and here back to the excited state and wavy line. So that's the non-rephasing contribution. And again, the last part, or the part of the omega tau of the response, because it's going to be a sum of two complex conjugated contributions, it's going to be a real part. So we can write again the A to the fourth power. All the transitions happen between the ground and excited state of the acceptor. There will be G omega t, that's supposed to be exactly the same. In the middle we have UGG t and real part of GAG omega tau. Okay, and now of course the same contributions we can find on the donor. So there will be corresponding, let's say, stimulated emission on donors and ground state bleach on donor signals. Okay, now what about the excited state absorption? We've said that there will be an excited state F. Clearly that is already a combined state, so this is not a state of either A or B or D. This is a combined state. So we look, however, we will try to look at the excited state absorption, which starts with exciting the acceptor. So there we will have the following. We will have the rephasing part will be exciting A, G, then exciting A. So now I am basically in a state in which the A is completely excited and D is not excited. But I want to have a rephasing signal, so rephasing signal has to end up with the wavy line here. but it has to have, as I have e to the power of I omega ag tau here, I have to have e to the power of minus I omega whatever t. This is how you get non-rephasing, because you have different signs of the phase here, of the phase evolution. So in order to have positive frequency, we can, for instance, have FA here. So I can do the following. I can excite to the F state and stay with A here. This FA has a similar frequency as AG, because, well, A is already populated. So if we look at this here, A is already populated. So the only thing that can be in addition populated is the D. So if we go from ground state of D to D, we build a state F which has both A and D populated. Okay, so that would of course mean that this is e to the power of minus I omega dgt. Yeah, because A is already populated and doesn't change, but from A to F you get by exciting D, and this is where you end up after the wavy line. So the signal is emitted from the coherence between the doubly excited state and the A, and this somehow, actually we will discuss it quickly, corresponds to the frequency, transition frequency on D. So because F is a combined state of both A and D excited, this is already a combined signal. So this was the rephasing part of it. The non-rephasing part of the stimulated emission on A has to be different, basically just by starting from the left hand side. Then we are supposed to get to AA, so that's here, and the rest has to be exactly the same. Here F, A, and then wavy line which goes to AA. No problem. All right, now what is the Liouville pathway, or what is the response function corresponding to this Liouville pathway? One thing very important to notice here, it's a stimulated emission and there is only one action from the right hand side, which means that there will be an overall minus in front of the response. There is a transition from G to A, so that's dA, and it's twice there, and then there is dFA also twice. We've already identified this with D, the transition dipole moment on the molecule D, but let's still write it as FA. So then we have the evolution FA and its corresponding sort of absorption line shape, complex absorption line shape. That's from the third, the most up interval. We evolve in the state of the acceptor, and because we are summing rephasing and non-rephasing part, we have a real part of G AG omega T. Okay, so now we have to make clear the identifications of the transitions from, for instance, from A to F. So what is dFA and GFA of omega T? So we can easily identify that the transition A to F is, that's the transition from EA GD to the EA ED. So in fact it's a transition GD to ED. It's a transition on D because nothing happens to A, and therefore dFA equals to D, and the dFA square dA square is actually nothing else than DD square dA square, and of course this is the average over all possible orientations. And similarly the GFA omega T is going to be, let's say, GED GD omega t, which is nothing else than g dg omega t. That's the line shape of the transition on the donor molecule. So altogether we can write that the SA is minus d square dA square g dg omega tau uAA t, real part a g omega tau. So here clearly this must be so. Here we have the excitation on the acceptor and emission on the donor, because, well, nothing else can be true in this picture. We first excite the acceptor stays excited, so when the next pulse comes there is only the D to be excited, nothing else can be left excited. Okay, so we clearly see that this type of signal is a combined signal and it involves both molecules, and we can also postulate the excited state absorption D, which starts on the D molecule, and we can also write its contribution. It's minus dA square dd square gAg omega t u dd dd t, and real part g dg omega tau. All right, that's nice. The only difference now between these two things, apart from being on different molecules, is that here we do not expect any evolution. Once you start on A, you stay on A, well, but once you start from D, you go to A. That means that there is a decrease of the population on D, and we can expect that this term here will actually decay exponentially with the rate KAD, and depending on T. So the ESA A and ESA 2 signals are composed of Liouville pathways that mix both molecules A and B, and that are connected through excited state evolution. But of course we can also have mixed terms that are connected through the ground state. Nothing can prevent that, so we have some ground state mixed terms, so that it has to be ground state bleach. So we are looking at some sort of a ground state bleach, that where the signal, for instance, starts at A and goes to D. So what that would be, let's draw some diagram. That means first of the signal, or first of the excitations, have to happen on the D molecule, so it will be a first and second interaction resulting in ground state again, and then the third interaction would go on A and the signal will be emitted on A. So we have to again find rephasing and non-rephasing contribution to this, and it's a ground state bleach. So when you are rephasing, you start from the right hand side on the D, so we excite the coherent including the excited state D, and then we have to go back to the ground state. So this is the second interaction that occurs, and we are here in the ground state. The next one has to occur on A, G, and wavy line produces signal. So this is clearly non-rephasing because it has evolutions e to the minus omega A G T here and plus I omega dg tau. That's what's making it non-rephasing, and it's a ground state bleach because the middle interval is in the ground state. The non-rephasing contribution has to have the upper part basically exactly the same, so it's gonna be this, but it has to start from the from left hand side excitation. So it's going to look like this, therefore, and that means that the last interaction has to occur from the left. So this has the same properties except of being a non-rephasing pathway. So if I combine these contributions together, then I get the GSB, ground state bleach, AD signal, which is basically, you see that we excite or we interact twice with the D and twice with the A. So that's the average of this transition dipole moment factor. The last contribution is AG omega T. The middle one is UG G G G. This will always be 1. There is nothing happening during the time that the system is in the ground state, and the combination of rephasing and non-rephasing signals give real part of the DG line shape. So this is tau. Okay, and very similarly we would construct also the DA contribution, where we start on A and end on D. It has to have the same prefactor. Here we will have DG G G G G T and real part of AG omega tau. Okay, and as I said, this is the evolution of the reduced density matrix in the ground state, and it doesn't change unless, of course, excited by the pulses, but the free evolution is just unity here. Okay, so this is a combined signal combined with basically almost no evolution in the ground state, but the interactions happen twice at one molecule and for the third time on another molecule. And of course we now have to also account for terms that are due to energy transfer. So far we didn't have those terms. All our combined terms always had evolutions that sometimes accounted for depopulation, like here, but they have never actually accounted for transfer. So UDD has to decay like this because there is energy transfer between D and A, but we haven't used the transfer term yet. So now we have to also construct the terms corresponding to the excited state transfer. So there is excitation transfer terms, and looking at the diagram of the levels, we can see that this should, for instance, involve the stimulated emission. For instance, like this, if you excite on the donor, so first two pulses will act on the donor, then the excitation will be transferred to the acceptor, and then on the acceptor we act with the third pulse and have a signal basically as the fourth appearance of the transition dipole moment. That will be the buildup of the signal. So this type of process already includes transfer during the population time capital T. So for instance, let's have a look at the rephasing pathway here, starting on the D. So it has to be from the right hand side. We have to get to the D completely. Now we have energy transfer to A, and now we have to end it up like a rephasing pathway. So we have to have AG here so that it's the opposite of the GD in the very first interval here. So we would have to, that means we would have to put an interaction here and the wavy line here. So this is again a positive signal which evolves with the term UAA DD. So this is DD going to AA. Well, how is that term looking like? It looks like 1 minus e to the power minus KADT. That's basically how this element looks like. Why is that? That's because DD decays, only decays. So its population is e to the power of minus KADT. And of course the other state, they together have to be 1. So 1 minus e to the power of minus KADT. That's the population of the state A, if the population at D was unity at T equals 0. So this is precisely the rising term that sort of describes the energy transfer. So now the stimulated emission term, which starts at D and ends at A, is looking at the diagram, and of course we also have to have a corresponding non-rephasing diagram. So let's quickly write it. It only has to start on the left hand side. So D, G, D, D, transfer to A, and then stimulated emission signal production here. Okay, so that's exactly the same rise occurs also in this diagram, and the total diagram, the sum of these two, will be therefore D square, dA square, and then AG as the final line shape. In between there is AA dt, and G, we first excite at D, dg omega tau, and real part of it because we sum rephasing and non-rephasing pathways together. Okay, so that's a term that we have to definitely account for. But there is yet another possibility how we actually can get a signal from a very similar setting. So again, you have donor, acceptor, we excite at the donor, the energy transfers to A, and there it stays. And because we are now in the ground state, so this is 1, 2, we can now, in the ground state of the donor, we can again excite from the donor and send a signal from the donor. But because this happens while A is excited, we are in fact reaching with the third pulse, we are reaching the state F. So this is going to be an excited state absorption signal. And again, real part of it should start at D, go to D with the second pulse, then we go to the state A, and while the state A is populated and we populate also D, that means we reach the state F. So here we have FA, which is an optical coherence of the opposite direction as the GD from the first interval. When the light gets emitted, we stay in the AA, so that's fine. This has the exactly same dependence on the time capital T, but you can see that this has a minus sign, and that's because only one arrow comes from the right hand side. And because again we have to add the non-rephasing part, but that's trivial, so we don't need to repeat it, but we can write the signal that comes from combination of the two. That's the ESA AD, because it started on D with the energy transfer to A. That's a signal which has a minus, and there is, you can see that all the transitions occur on D, so this is D to the fourth power, it's G, D, G omega T, because the last transition is basically same as the transition D, G, for the reason that F is basically composed of both A and D excited, and the G here is from the state A. Okay, so the last one is G, D, G. The middle interval is AA, D, D, T, and here we have real part of G, D, G omega tau. That's the ESA term. All right, and this is all. You can try to check this, try to figure out if there are any pathways that we forgot, but we hopefully didn't. So sum of all these pathways builds the signal. So we have a total spectrum as a sum of all these pathways. And now let's try to place all these signals into this two-dimensional plot that we have. So placing the signals. So we first realized that the real part of GAG of omega is basically the absorption of the acceptor as a function of omega, and we can define a line shape centered at 0 with tilde so that it will be written like this. So by this I can show where is this line shape centered. So this is centered around omega A. I mean, in principle we could also assume that both the line shapes are the same, and then we would write just omega tilde omega minus omega A, and the position of the spectrum is determined by the omega A only, and there's one and the same line shape, although A and D can have different line shapes, so we can also use the subindex A and D to distinguish these two. Okay, the same will be true for the real part of GDG omega. That's some alpha D omega, and we define alpha D, which is centered around 0, so that this is the way that we place the spectrum to the right place. Now let's draw all possible line shapes. We of course mean in this dimer line shapes and positions. All possible line chains and positions in what? In a two-dimensional spectrum where we draw omega t here and omega tau here. So omega tau is the excitation frequency, omega t is the detection, or in other words emission frequency. So we have omega donor, the higher frequency, and omega acceptor here, and we also have them on the other axis. So this is A, omega D. And we have two-dimensional line shapes that look like this. So for instance, here at AA, I will have a product of alpha A, omega T, alpha A, omega tau. So two functions that are basically the same, placed both around the frequency omega A. So we will have a symmetric picture like this. Let's use some sort of a contour plot. The other situation that can occur is that we will, for instance, have alpha D at omega tau. That's a function placed around omega D, multiplied by alpha A at omega T. That's a different function, but they are similar, so we can have a spot, have a contour place also here. And the same will happen here and here, by the simple fact that we can have alpha D omega T and alpha A omega tau, and here we have alpha D omega T and alpha D omega tau. These are four line shapes that can contribute with plus and minus signs, but only these four spots can be actually seen in the 2D spectrum. We can also copy the axes here and draw the absorptions. So this is alpha A omega tau, alpha D omega tau, and here we would also have alpha D omega T and alpha A omega T. Okay, so this is how we kind of conceptualize the 2D spectrum. If we look at it from the bottom, we should see the absorption spectrum. If we look at it from the side, we should see the absorption spectrum also. However, these things are connected and weighted by the evolution superoperator, describing the energy transfer between the states A and D. Okay, so this was theoretical, where and what to place in our 2D spectrum, but now we have to put them with the right prefactor and connect them correctly with this evolution superoperator. So let's now construct really the particular spectrum that we are after. So the spectrum of the donor-acceptor dimer. This already is the particular case that we are investigating, so let's draw again the same axes, and omega A, omega D, omega A, omega D. So now we will just draw 4 spots, and let's write next to these stops what signals we expect to see. So let's go up where we started to draw the first diagrams, and let's put them into the right spot. So for instance, here the stimulated emission on A absorbs and emits on the omega A, and there is no time evolution. So we find the place which absorbs and emits at omega A. It's the stimulated emission of A, and that goes to here. Then the next thing is the ground state bleach of A. Ground state bleach of A, again the same line shape, so this belongs to the same spot. So plus ground state bleach of A. Well, we can also immediately say that when it comes to the stimulated emission of D, it has to go to this spot, because it has line shapes of the omega D, or centered around omega D, and there is also going to be ground state bleach of D, which is completely unmoved. It's a constant contribution that again sits on this diagonal position. So that's what we get from this first set of pathways, but right after those pathways we got the excited state absorption from A. An excited state absorption from A we have identified to start at A and end at G, and it comes with a minus. So starts with A and leaves at D and has a minus. So there's gonna be minus ISA A at this spot. Okay, then we have ISA D. ISA D, like ISA A started on omega A, the ISA D will start with omega D, and it has to occur, it has to emit on omega A. So that's this position. There's going to be minus ISA D here. Okay, let's have a look what are the other contributions. So ISA A, ISA D, we have already seen that these contributions end up outside the diagonal of the spectrum, and that's because they are mixed. They are mixed contributions, involve both transitions on the D and A molecule. All right, so the next ones were contributions that look like the ground state bleach dA. So they started on D. Actually, in our convention, because they started on D, they would have to be denoted like this. So ground state starting on D and going to A, well, has to be placed. So this is here and here. It's from D to A and from A to D. Okay, we can use both of them already, and if it starts at D and goes to A, so then it has to be down here. So this is going to be plus ground state bleach starting at D and going to A, and here plus ground state bleach starting at A and going to D. And the last type of signal that we have seen, so is the one with the excitation transfer, stimulated emission dA. This one starts at D and emits at A, starts at D and emits at A. So that's also here plus stimulated emission starts at D and goes at A. And the last term is excited state absorption, starting at D and going to A. But here, very interestingly, both line shapes are at D. So this is also going to contribute exactly as it says at the D. So this is excited state absorption. So it's with minus, that's S. So minus is dA. Okay, so we have written out now which contributions contribute to which positions in the spectrum, and we have also noticed that there are some minuses here. So now the last thing, we don't have enough space on this picture, so the last thing would be to actually place them with the right prefactors that come from the transition dipole moments, and also with the right time evolutions. So having this picture in mind, we now try to construct 2D spectrum with, let's say, some rough formulas for the amplitudes of the individual peaks. And here we have to stop because we ran out of time, and we will continue in the next video.